Hi and welcome to video 3 on my video series to do with binomial probability, mathematical methods, unit 4, topic 3. And in this video we're going to just finish off our work on discrete random variables by talking about some other variations on calculating expected values, variance and standard deviation. So just recall that video 2 led into that, the basics, setting up an expected value calculation and a variance standard deviation calculation using a table. And in this video we're going to extend on that, so you will need that knowledge from video 2. So in video 2 we talked about the fact that this is how we can calculate the expected value by determining the sum of all of the data points, x, by the probability of those data points. It's a fairly simple calculation, one line in the table. The expected value may also be calculated like this, where you're doing the expected value of a function as a function varies. So your x might not just be a linear set or a random set of numbers, it might be based on that value within a function. But as you can see, it's the expected value of x equals x times the probability of x in each case. So it's really the same thing. It's just where your values are represented by a function, and you can have a look at the textbook for some more detail on that. What's going to be more important is this one here. The expected value of a linear function, so where a function varies, and we'll have an example of this later, is can be simplified to be a times the original expected value of just x plus b, where the linear function is ax plus b. So the linear transformation of a probability distribution works exactly as you would expect, so make sure that you're aware of this. Variance is slightly different now. We've discussed and shown an example in video 2 of variance being the expected value of x minus the average squared. So you sum up x minus the average squared times by the probabilities using that expected value formula up here. Sorry I'm ruining this page with pink pen, but I'm just trying to point out what I'm talking about at the time. And so that is this variant. That's the expansion on that variance of x, and that's what we talked about, and we did an example of that in video 2. The variance of x can also be calculated like this. If you go back to your original variance and standard deviation formulas, you'll note that there are two ways of representing them. One is where you sum up all the x minus mean squared, divide by the number of numbers, or if it's a sample, the number of numbers minus 1, take the square root, and that aligns really closely to this method. And the other is to do with the fact we can separate the mean and the data points and find the sum of those things squared individually, and that's this option here. So it may be easy to calculate, and you just need to be aware that you may be given things like you may be told these things, and so it may end up being a bit easier. But more importantly is this: if we're trying to find the variance of a linear function, then it's equal to a squared times the variance of x, the original variance of the function. So again, this could be a really simple multiple choice question, an external exam, or a 2-mark question where you're told the variance of x and you want to find the variance of a linear variation on x. Shifting a distribution up and down by b has no effect on its spread. That's why that b doesn't come into play. And of course the standard deviation down the bottom here, the standard deviation is just the square root of the variance. So everything you do with variance, we do the same with standard deviation, we just take the square root. So in this case that would be just a times the standard deviation. A times standard deviation of x would be the standard deviation of ax plus b. But I would probably stick with finding your variance first and taking the square root as required. We're using the Cambridge text, so it's just important to note that some of the exercise references this idea that 2 standard deviations from the mean is where approximately 95% of the data lies. It's a pretty good approximation as long as you have a large number of data points. We will talk more about this as we move forward with the topic. In particular, Unit 4, Topic 4 does address these types of ideas, and right into Unit 4, Topic 5. That's normal distributions and confidence intervals. So we'll get there, but for now, you may be asked some questions along those lines. So let's have a look at example 3 and example 4. Now example 3 is just a reminder of our work from last lesson. So just recall that the expected value of x is equal to the sum of x times the probability that x equals x, and the variance of x, we need to find the standard deviation as well, the variance of x is equal to the sum of x minus mu squared times the probability that x equals x. Of course, mu is our variance, is our expected value. It's our mean. So let's set this up. First of all, I'm going to do x times the probability that x equals x to find my expected value. So I get 0.2, 0.8, 2 times 0.4, 5 times 0.1 is 0.5, and 8 times 0.3 is 2.4. And when I sum those together, I get, therefore, the expected value of x is equal to the sum of x times the probability that x equals x, and that's just the sum of those four values there, which is 3.9. That's my average. That's my mu, and that's what I'm expecting to get if I do this heaps of times. I'll get on average 3.9, and that's good that it lies somewhere in the middle. That means it makes sense, so we're happy with that. And the second part is to find the variance. So the variance, remember, we just build up this formula here where mu is 3.9. So the first thing I need to do is work out what x minus mu is. And so my x is 1, 2, 5, and 8. I get negative 2.9. That's 1 minus 3.9. 2 minus 3.9 is 1, negative 1.9. 5 minus 3.9 is 1.1. 8 minus 3.9 is 4.1. So expect because we're taking away the mean, we should find some negative, some positive, and they will add to give 0 if you add them together. And then we need to do x minus mu squared, and I've got a calculator to help me with this. So 2.9, remember if we square a negative we get a positive. This is 8.41, and 1.9 squared is 3.61, and 1.1 squared is 1.21, and 4.1 squared is 16.81. Then we need to get those and multiply them by the probabilities. Some will be easier than others. Remember, our probability line is this one here. So 8.41 times 0.2 is going to be equal to 1.682. 3.61 times 0.4 is 1.444. 1.21 times 0.1 is 0.121, and 16.81 times 0.3 is equal to 5.043. And if I add those together, so this is my x minus mu squared times p of x equals x, and the sum, so the variance of x is equal to the sum of x minus mu squared times by p of x equals x, and that's just the sum of those numbers, which I'll just do quickly. 1.682 plus 1.441 plus 0.121 plus 5.043, and I get 8.287. Now the variance doesn't really match too well with the data. It's greater than a whole set of data, which doesn't help us too much. The range of this data is 7, but the standard deviation is usually a little bit of a better measure. So the standard deviation of x is equal to the square root of the variance of x, and so I take that answer and I calculate the square root of that answer. So I take the square root of 8.287 and I get 2.88 approximately. It's quite a large number of decimal points because it's the square root, and 2.88. Two standard deviations either side of the mean should encompass about 95% of the data. In this case, it's not a very symmetrically set of data, and that 2.88 times 2 either way gives about a range of 10, so it actually encompasses all the data, but we're pretty happy with that. So there's my calculations of mu, my expected x, and variance of x, and the standard deviation of x from the variance. Now, moving into example 4, we're asked to use the answers from example 3 to determine the expected values, standard deviation, and variance in each distribution below. So I'll just create a little bit of space between them, and then we can start working them. It hasn't taken the B with it. My apologies. Seems to not want to take the B with it, so I'll just take these separately. There we go. Okay, so first of all, it's good to recognise here how the set has changed. So if I just do some rubbing out here and just take the set with me so we can see, I'll just put it over to the side. Copy that. Ooh. My apologies. And just bring it to here. So I've got 1, 2, 5, 8. Hopefully you can see that in this case we're actually calculating the expected value of 10x, because x is just multiplied by 10 in every case, and so the expected value of 10x will be equal to 10 times the expected value of x, which will be equal to 39, and the variance of 10x will be equal to 10 squared times the variance of x, which will be equal to 828.7, and the standard deviation of 10x will be equal to the square root of 828.7, which will be about 28.8. So you can see where we're getting here using that linear modelling to help us do those corrections. So we'll do the next one, see if C moves with it, and it has, that's a bonus. So in this case, I'm looking to see what's happened here. I can see that it's had 60 added to each x value, so therefore the expected value of x plus 60 is actually equal to just the expected value of x plus 60, which equals 3.9 plus 60, which is 63.9. The variance of x though, the variance of x plus 60, remember that b doesn't make any change to the actual variance, so the variance stays the same at 8.287, and therefore the standard deviation, which is the square root of variance, will also stay the same as the original amount, which was 2.88. So no change there. So you can see these are quite simple, easy to manipulate questions once you understand the rule. And in this case, if I have a look, there is a linear rule here. X goes to 2, 2 goes to 7, 5 goes to 22, and 8 goes to 37. So you might need to have a play around with this, but if I have a look at 1 to 2, and then 2 to 7, and then 5 to 22, and 8 to 37, well, so you can see as I move on to the next one, I'm adding 5. That tells you that there's a multiplication factor of 5, so x is actually going to 5 times x, and then to get it back down from 1 times 5 gives me 5 to 2, I'm subtracting 3, and 2 times 5 is 10, subtract 3 is 7, and 5 times 5 is 25, subtract 3 is 22, and 8 times 5 is 40, subtract 3 is 37. So you might have to play around with that, practicing building linear functions from those relationships. Just by working out the gradient between 2 points, and then you can always just substitute a point in as if it's like an x, y function to determine the overall function that's coming there. So anyway, that's what x is going to, 5x minus 3, so we have our expected value of 5x minus 3 is equal to 5 times our expected value of x minus 3, and that's 5 times 3.9, which is 5 times 3.9, 19.5 minus 3, so that's 16.5, and our variance of 5x minus 3 is equal to 5 squared times the variance of x, and so that's equal to 25 times by the original variance of x, which was 8.287, that's 207.175, and the standard deviation is the square root of that, 5x minus 3, or just 5 times the original standard deviation is the other way that we worked out we could do it as well. And so 5 times the original standard deviation of x is 5 times 2.88 times 2.88 is equal to 14.4. And so there we have some examples of building up that understanding. I'm not going to go to the complex unfamiliar question here. I'll do that in class and you can refer to the OneNote to look at that. But for now, there's some understanding of what you need to know for this topic. All the best.